All right, this is H is for hacking. I'm going to talk a little bit about circuit bending. The example I have didn't really go as I had hoped it had, and so it's going to be a little bit more intimidating than maybe sometimes circuit bending can be. So as I go through here and I start to talk about things, please don't be like, oh, that's past what I can do, because it's really not. I think anybody in here can do this type of stuff. I'm also kind of OCD with some things, and maybe I went a little harder than I needed to and made it a little bit more difficult. And I'll try to point out those points where, like, you could shortcut here and it would be a lot easier. So yeah, that's this course. Quickly about me, I do a lot of RE, reverse engineering stuff. So that's typically where I live. This course isn't really my, like, I don't do a lot of hardware. I do some hardware and physical pen test attacks, but this really isn't like, this is more of a hobby for me, not a line of work. So see Exhibit A. This is what I will be talking about today. This is the toy that I chose to pick on. I have a 2-year-old at home, and you see this nice little, we call it an E-pad. I don't know what it's really called. What is it? Yeah, its name is too long. But it's a nice little device. It's got little letters on it, and each letter, you know, H is for something, and then it plays some music and it lights up around the edges. But I wasn't quite satisfied with their choices of letters and what they stood for. You see that S? Anybody can guess what S stands for? S stands for sister. Come on, guys. This is like a baby's toy. Don't you know that? S stands for sister. That image is clearly your sister. Yeah, it was things like that. I was like, this toy annoys me that I'm going to replace this. And so I'm going to replace this as S stands for security, right? And A stands for accountability or authentication, right? And so that's what I wanted to have. I wanted to teach my kid from the go, like, these are the terms you need to know to make it in the cybersecurity world. Like, you'll be set. But my goals with this is I didn't want to overdo it. I ended up overdoing it a little bit. But I wanted to replace it with hacker-themed letters. I wanted to reuse as much of this as I could, right? I didn't want to make my own PCB board with, like, buttons on it, because that doesn't look as cool as this. Like, I liked the screen. I wish I could change the pictures. Maybe I could have, like, somebody draw over the top of them. But I wanted to reuse as much as the frame, the pieces there, and I wanted to keep it simple. I didn't want to do something really crazy. So, step one, we take it apart. This is the inside of that. There's not a lot there. In the bottom right, I have to look at my hands. In the bottom right corner is this flexible line that comes from the screen, and it's got 28 headers on it, and it's just pushed against the board with a piece of foam underneath it. And then you can see on the board, those gold plated pins, they just marry up. And that's how it interfaces with the keyboard. You see a speaker there, and that PCB. That PCB is one-sided. In the top right is the backside, and there's no traces on the backside. So that's a pretty simple-looking PCB. All the traces are on the front. I can just look at, it's got an LED on the corner too, and then you can see the wires to the battery. So we're going to tear down. We're going to look at what I need to do, or what could I do to attack this. First, maybe I want to talk back a little bit. I got these in the wrong order. Let's talk about this black blob. This was disappointing for me to see. So this is called chip on board. And typically it's done as a cost-saving measure, even though it turns into be a really strong security measure for hardware attacks. Because basically this chip doesn't even have a casing on it. It's just the tiny little part and little fingers that are built right on the PCB on production, and then they program it there, and then they put the blob down to protect it when it's done. And it's extremely hard to attack, right? Like, you need to sand it down. It's just beyond what I was going to do for a kid's toy. I don't even know if I could do it if I really wanted to. The attacks on those are really, really difficult. Furthermore, there's no identifying marks. So I can't even figure out what processor it is, if I can make attacks on it. That kind of limited what I could do if I wanted to attack this board. You will find these very often on cheap, mass-produced things, because it's cheaper for the producers to use these rather than complete chips that have the casing and all that. Like, it's a penny's savings, but, like, when they mass produce these, those pennies add up, right? So that means I'm not going to be able to modify this chip or, like, reprogram it. I'm going to have to come up with my own chip. And so this is my first thing, like, oh, wait, I'm not a developer. I don't do hardware development. I can't do this. Yeah, you can. It's not bad. Furthermore, if I design my own PCB as a replacement for this, You don't have to do that, right? Like there's a micro Arduino that would fit right inside this case that you could use. If you don't want to do that, you would just have to glue it however you want. But I wanted to be like, I want to be just right fit like that board. And so that's where this slide comes in, is I wanted to reproduce a board that was just like this one. I could fit right in its place, but with my own processor so that I could do whatever I wanted. Now, PCB design, again, isn't that hard. There's plenty of talks at this conference where they talk about making mini badges or like intro to making your own mini badges. This is just that, but on the next level. Now you don't have a mini badge design, you just have a board you're trying to make a copy of. It's really not much different. So if you attend, I would highly recommend you attend those mini badges talks and just try making one. They're not that bad. It's like altogether maybe a $50 investment, but it's really interesting to learn and it's not hard. So anyways, so first I wanted to do is I needed to get the dimensions of this thing. You notice in the bottom right corner, there's a little cutout. You need to measure that and get around the screw so that I could fit it right in that exact same spot. I also needed to measure where each of the little screw holes were to put the same screws in so I could make it fit in the exact same spot. So here's the MCU. What I decided to replace this with was a Raspberry Pi Pico. That's a really friendly hacker chip because it can run CircuitPython, and it's really cheap. It costs like $1. I think it's not in mass, it's like $1.25. It's really not bad, especially right now. It's really nice because there's actually stock. Like all the Arduino chips, the Atmega chips, they're really hard to get a hold of right now, even still after 2020. So that's the reason why I went with that chip. But I don't want to replace the keyboard. That means I need to interface with that exact same pin layout, right? And I told you it had 11 pins. I need to place my same kind of pin headers there, and I need to know how that works, right? There's 28 keys on the keyboard, but there's only 11 pins. And so a common thing, and when I say common, it's like I don't expect you to know this. You can Google this when you've got like a toy you're taking apart, right? Like a keypad or number pads, they typically do what's multiplexing, where you can see in the bottom right here, there's one pin per each row and one pin per each column, and you take turns powering each row and then looking at each column, and if any one of those columns is like you make a row high, and if one of those columns is high, then that means that corresponding button has been pressed. And that's how they do this to cut down on having, instead of like 28 different wires you have to wire, right? You can just do number of rows plus number of columns, and that's how it works. So this has 4 rows and 7 columns. That makes 11. I looked at the board. Looking at the board, you can see these 4 capacitors, these tiny little C somethings at the top, tied on 4 of those. That made it really easy to let me know, hey, these are probably the 4 rows, and the other 7 are the 7 columns. And then you could use a multimeter to test that. I never did because I was pretty confident that's what it was, right? And it would take like 3 hands, one to hold each lead of the multimeter and one to press the button. But you can do a multimeter to test your assumptions when you're designing it. So that's the keyboard interface. Let's talk about the other things I see on the circuit. I'll start at the top right. We got an RGB LED. It's got 4 leads. That's pretty simple. 1 for each of the 3 colors, and then a common one for either ground or power. We talked about the keyboard already. There's the power switch that's on the back side. You can flip it over and marry up those headers, right? And then there's a switch at the bottom which lets you like select different difficulty levels of the alphabet. I'm not sure what it did, but I'm going to have it select different letters or different values for each letter. That's optional. And then everything else is almost there. I'll talk about the LED relays in a second, but you can see all the traces and follow them at least back to the black bob. So I could see everything that this circuit was doing. It was really nice that I didn't have to like follow traces from one side through a via to the other side. It's all on the one side. Because it's on one side, when their traces need to cross over each other, like usually when you're making a PCB, when traces need to cross over each other, you have one go to the back side, and you're like, kind of like sewing, right? But since they only have traces on one side, they had places where they had to cross over. I see these yellow-lined bridges. Those resistors are all marked 000, which means it's not a resistor, it's just a wire. So everywhere one of those resistors are, they're using that resistor to hop over a trace line. And a technique I don't see very often, but it was kind of funny, so I thought I'd point it out. And then the LED relays. The relays are just there so that the LED doesn't draw too much power. That's not necessarily needed with a CircuitPython. I mean, if you've played with an Arduino, I think you're like, okay, I could pretty much handle each one of these things by themselves. I can turn on an LED. I can understand like powering a row and checking the button back for the keypad. I can, check a switch status, and I can probably speak to a speaker. I could send audio output to a speaker. So I was like, cool. I can handle most of these things myself. My first attempt, I failed, and the reason being is that board didn't have any kind of audio amplifier. And I didn't think about that when I made mine. So I made mine, and the audio was like extremely quiet because there was no audio amplifier. Whatever chip they're using under there must have a built-in audio amplifier, and I just wasn't aware. So on my first board, I have the board, and then I have like an audio amplifier, like a little, Arduino module on the side, and then I made a second attempt. It's one of those things that I should have known, and I just failed. But the other thing I wanted to add is I wanted to add a USB port so that I could not just like build it once and then put it together and not change them. So I wanted to add a USB so I could change the files on the fly. The cool thing about a Raspberry Pi Pico, which by the way is the same processor that your or your SAINTCON badge is using, it supports if you're CircuitPython, and that CircuitPython, like when you plug into a USB, it'll show up as a drive. Mike's done a lot to make that not there because he's hiding things and he's not even using CircuitPython. But you can reflash the badge with CircuitPython, and then it will show up as like a mass storage device. And you can just upload files to it. You can upload the Python file to it, and it'll just run your Python file. So CircuitPython is really quite easy. I think that's my next slide. Yeah. CircuitPython is really quite easy. If you know Python, you can just write some Python code, you save it, and it starts running your Python code. I can just drag and drop WAV files to a directory and play those WAV files from a directory whenever a button is pressed. It's instant feedback. I don't got to compile it and then put it on the thing. And so really, really, really friendly. I highly recommend. There's like $4 Raspberry Pi Pico development chips that you can buy from Amazon. If you're just slightly curious, $4 is not much. Just buy one and try playing with it. Try running CircuitPython on it. Adafruit has some great documentation or great tutorials on how to play with that chip. And for $1, it's really quite cool. Okay, so now with all the pieces, so let's design the PCB. Like again, I'm not going to talk much about this, but on the left side is my schematic layout. The big box is this Raspberry Pi. That's really tiny font. And then to it needs a clock. And then there's the programming header is not even needed, but I put it there just in case, but I never actually used it. And then I've got leads to, you can see the speaker and the amp and the USB and the switches. And then on the right is as I laid it all out, I had to make sure that my pins for the keyboard and the screw holes were right, but then other than that, I could place everything else where I wanted to. So here's the comparison of the original board, and then here's my board with the modifications to the side. You notice the little spot for the USB sticking out on the bottom. I think I had that back here. I had to modify my original toy to make that little output to fit that. And then even so, also the cutout for the plastic that was there, I got my dimensions wrong. And so I had to take a Dremel and kind of make that hole a little bigger. It wasn't quite pretty, but it worked. So it's pretty simple. I just have a microphone. I record what I want to say. I let my kids record what they want to say, and then just upload that to the mass storage device, and it works. And that's my kiddo deciding that he liked it. To be honest, he had more fun putting his own audio on there and then just listening to himself. Right? He loves just pressing the same button and listening to himself talk. He got that from me. But yeah, he had a lot of fun with it. But the real point with this talk was that we have that toy and plenty other toys and other real devices at the hardware hacking village down in the I don't know, the area, the fun area. So I would love for you to come down and record a letter sound. I have the audio down there. But more so, there's a lot of different toys down there, and I can show you how to make attacks where you don't have to replace the circuit board. We can pull the firmware off a little different toys. We can talk to a UART port if you've never done that before, and we have JTAG pings on some things. So really, if you're curious about this kind of thing, or you have questions, or you have your own device that you would like to attack, the goal with the Hardware Hacking Village was like, bring it there, and we'll figure it out together. If you're curious, you have something you've started, or you just want to play with it, please come down and visit us. That was kind of the point of this talk. So I really appreciate you guys taking the few minutes to be here. I know it said it would be 30 minutes, and I rambled really, really fast. But yeah, do you guys have any questions for me right here? I kind of went pretty quickly. Yeah.
What program did you use to design the circuit board, and how did you get that fab?
Yeah, so he asked, what program did I use to design the circuit board, and what else?
How did you fab the circuit board?
How did I fab the circuit board? So I used KaiCAD. KaiCAD is free open source tool for designing electronics. It's a beautiful tool. I used to use Eagle, which is a commercial product, but KaiCAD is much better, and it's free. And so KaiCAD has common footprints. KaiCAD can even give you a 3D model of your tool, like after you designed it. And once you design it there, I sent it to, I sent it to all PCB in China to get it fabbed. That's mainly because they were cheap. There's a US one, OSH Park, which charges you by the square inch. So if you're doing something small, like a mini badge, OS Park's pretty cheap. If you're doing something big, OS Park gets way out of price. The fab for this, it's like, I get 5 boards for, it was like $13, and then shipping's on top of that. So DHL is gonna be $20, and the post-rate shipping's like $5. So depends on how big of a hurry you are. Most of the Chinese shops are cheaper, but they take forever. Yeah, that answer your question? Yeah, I really would encourage, I think Compuk is teaching a course on mini badges here somewhere. If he's not, I'm gonna go yell at him. But he should be, because that course really teaches intro to like designing a board, and like you've already got a good footprint, right? Like it takes care of a lot of the hurdles for you. And then once you've designed one, your world opens up. It's like, oh, I could do anything, right? It's pretty cool. So take his course if you've never done one before. Any questions? Any others? Great. Thank you guys for coming. I hope it was at least something that you were kind of interested in. Maybe it didn't go the way you thought, but thank you again for your time.